Let's understand the context of this question. This question is about a wave traveling from point S to another point P. So there were two situations. In the first situation, it was one consistent medium from source S to point P. And in this consistent medium, the speed was v, while the wavelength was L. In the second situation, the source S and the point P is still the same as before. However, along the pathway, a portion of the original medium was replaced by another medium. And when this happens, the speed decreases to become 0.70 v. Since the source S remains the same for both situations 1 and 2, and assuming that frequency has no change for both situations, we will expect that the wavelength in the second situation, considering the new medium, it will be 0.70 L. So the question says that comparing situation 2 to situation 1, there will be a change in phase of the wave arriving at P. So why does this change in phase of the wave arriving at P occurs? If you are sharp enough, you realize that the difference in wavelength in that particular portion is the reason why there will be a change in phase of the wave. Let's better understand this with some illustrations. So let's compare situation 1 and 2 for the same region. So let's call the left of this region to be X, the start, where it starts to move into the wave start to move to the region, and the right side where it starts to exit to be Y. Similarly for situation 2, it's the same X and the same Y. So for situation 1, the wavelength is L, so let's draw maybe the wave to be having this particular width. While for situation 2, the wavelength is smaller at 0.70 L, so we can draw a thinner wave. So basically, if you look at this XY region, first thing you realize that at the X point, for both situations, the phase are actually the same. However, because of difference in wavelengths, at the exit point of Y, the waves may not be in phase for both situations. For example, considering situation 1, let's say that the wave ends at a crest at point Y. For situation 2, however, because of the smaller wavelength, when it comes to point Y, it may not be at crest, but maybe it is at the 0 point. So with this, we can see that at point Y, the phase may not be the same. So now let's go back to the question and consider what the question wants us to find. The question wants us to find the change in phase of the wave arriving at P, comparing situation 2 to situation 1. By this case, it's obvious that we can't find the phase at P directly because we have no distance for S to P. So however, what we can do is, since we know that the change actually occurs because it's between X and Y, we can consider the phase difference at X to Y for situation 1 minus the phase difference at X to Y in situation 2, and that should give us the answer that we want for the question. So let's use the phase difference formula to find these two phase difference X and Y. Let's consider for first situation 1. So basically, we know that the phase difference between X and Y in situation 1 over 2 pi is equals to the distance xy over the wavelength in situation 1, which is L. Since we know that xy is actually 20.5 L, we will get the phase difference at X to Y in situation 1 to be 41 pi. Now let's consider for situation 2. So we're going to find the phase difference of X to Y in situation 2. We use the same equation and formula. So it's over 2 pi is equals to the same xy, 20.5 L. By this case, the wavelength between X and Y is 0.70 L. And this will give us theta xy 2 is equals to 58.57 pi. And therefore the answer we want is actually 58.57 pi minus 41 pi, which gives us 17.57 pi. But notice that 17.57 pi is not one of any of the answers. So what we need to do is we have to reduce this into an equivalent small angle. This is simply done by just minusing away 2 pi's until we get an answer that's more than 2 pi. In this case, if you minus enough 2 pi's, you realize that you get an answer to be 1.57 pi. And therefore, option 2 meets our situation.